Ladies and gentlemen, welcome to our seminar. For those who are first time here, I would like to remind you that this seminar is very important for our university because we invite very famous and prominent speakers from all the world who are willing to share their achievements and passions with us and inspire to professional and personal development. At this point, I would like to give a big thanks to Academia Europaea Hub for invitation for our distinguished guest. And Academia Europaea since November is our patron of our seminar. Thank you. Before lecture, I would like to say a few words about our speaker. Professor Don Dingwell is a professor of mineralogy and petrology at Ludwig Maximilian University of Munich and director Earth and Environment. Yes, he has about 600 papers on geomaterials. His approach is fundamentally experimental and material-based. He holds 12 scientific awards, 8 academic memberships, 6 honorary degrees, and 3 national orders. He was president of the European Geoscience Union and Secretary General of the European Research Council. He is currently president of Academia Europaea. Professor will give a lecture titled From Experimental Geoscience to Lunar Geoengineering, and he will talk about research on space-sourced building materials. Professor Don Dingwell says about his talk, "Now we are stand on the threshold of a new challenge, the engineering of lunar and eventually the Martian surface. Tremendous multiple research goals await us, including the generation of water, oxygen, helium, and structural building materials on the moon, all using local materials. The expertise from decades of high-temperature manipulation of melted rocks in order to understand volcanoes is a near-ideal preparation for this talk. I will try to explain where we stand in this exciting area," Professor says. Professor, welcome to the stage.
Thank you very much for the very, very kind introduction. So as you've heard, my name is Don Dingwell. As you can hear, I'm not from this continent. I'm from North America, but it's okay, I'm Canadian. And from the island of Newfoundland, where if I spoke with the local accent, you would not understand me. So let me use my neutral English if I can. I've been in Germany for 40 years, and I've been working in experimental work the whole time. Germany was sold to me as a kind of a paradise for experimental physical sciences. It was more or less true. That's why I came to Germany, and that's why I stayed in Europe. So I just put up this first diagram, which is to say that a lot of what I will say in the following slides is in this one paper, which is open access. So, and this paper is written at a very high level, at a very simple level, so that anybody can get something from looking at this paper quickly. And if you've understood basically what I say in this paper, then you understand everything I'm going to say today, and you also understand how I think, how I work, and so on. So we've summarized in our past research in the field of mineralogy, petrology, and volcanology, this very special state of matter, the molten state. Liquids are indeed some of the most interesting physics of materials, because liquid structure and how liquid structure plays into liquid properties is still wide open. There are many theories, but none of them are completely convincing. So very different than the crystalline state, very different than the gaseous state. These complex liquids are an active area of research in physical chemistry, in physics, and as you'll see also in glass science. And so here are just 2 books which summarized the state of the art, one 25 years ago and the other one a couple years ago. And I hope you see from the cover of the one on the right, the inspiration for us, of course, is always the fact that the Earth gives us these liquids routinely at the surface. It's an amazing thing about our planet. And that we can understand them with very different methods of investigation, with simulations, with microscopic work, with scanning thermodynamic properties, and with spectroscopy. So all of this work began for me in the field of, I'm not trained as a volcanologist, but I've applied myself to the problems of volcanology because in Europe it's a very important problem. About 10 countries of Europe are responsible for a volcano somehow, somewhere. Some on the European continent, like in Greece, Italy. Some further afield, like in Iceland. And of course, old territorial possessions, as we would have said in the old days, of France, of Great Britain, of Spain, of Portugal, the Azores, the Canaries, Madeira, and so on and so forth. And so it's a very active area of research and research funding in Europe. And we began looking at this from a materials point of view, which was to take a kinetic property of these liquids, which is the time scale for the relaxation of the structure, the time scale for the structure pulled out of equilibrium to find its way back to equilibrium, a so-called relaxation time scale of the structure, as a function of temperature. In an Arrhenian sense here, so cold is on the right, hot is on the left. And what you see is something in the middle in yellow, which is called the glass transition interval. And this glass transition interval is simply the kinetic freezing out of the relaxation of the liquid. So everything to the right of it is a solid, is a glass, and everything to the left of it is a liquid. And as you can see, because it's a slope on this diagram, it's fundamentally not a thermodynamic variable, at least not of the first order. It is rather a kinetic or a dynamic property of the system. Its location in temperature depends upon the time scale of an observation. And it's a beautiful example of such a phase transition in nature. So we've taken it to the field because what we get from volcanoes is the following. We get liquids arriving at the surface of the Earth, and when we go to investigate the debris that these systems have produced, we don't find liquids, we find glasses. And so it's one of the most natural places to look for the attributes of the glass transition and to look at whether the glass transition can tell us about nature. And what you see here now is an example just to remind us why we do experiments on volcanoes at all. We can get fairly close to volcanoes. This is an example of getting close to the volcano Stromboli. And you can see, if you're really lucky, you have an amphitheater and you have a vantage point from above, and you can see a lot, but everything you see is above the surface of the Earth, of course, and you cannot see what's below the surface of the Earth. Yes?
Do you just wait around the volcano for it to explode, or do you have somehow trigger the eruption?
In Stromboli, we have the fantastic example of a volcano which is rhythmically and routinely exploding. It means it's in a phase of active volcanism. So actually, we would say that Stromboli is the great volcano to go to study, to learn volcanism, because you could be guaranteed to see an eruption, if they let you in. Huh? So we tried to do these explosions and the production of volcanic ash in the laboratory, and we were the first to be able to produce glass in the form of fine-grained material, which we call volcanic ash, which is what explosive eruptions produce all over the globe. And these eruptions can be enormous. They can have global climatic effects, which run over years. So Europe was cooled in the early 90s by one eruption in the Philippines called Pinatubo. And it was a small eruption. And we have in Indonesia the largest eruptions that we know about on the human time scale. Toba, 70,000 years ago, thousands of cubic kilometers of dense rock equivalent. I think you can imagine what dense rock equivalent is. It's literally the unexploded block, a kilometer on a side, thousands of those produced within days. It's the largest energetic event which is endogenous to the Earth, which comes from the interior of the Earth. It's larger than the largest earthquakes on the surface of the Earth in terms of energy release. The only thing which is larger in the Earth system is extraterrestrial impacts, which in the past, of course, have been enormous in size. So you see here our experimental laboratory, our experimental volcano in the basement downtown in Munich. And you can see here a tank, which is our atmosphere. And you can see below it, right here, a blow up here, and you can see it's glowing red hot. So we can obtain the temperature, the pressure, and also the time scale, the decompression rate and time scale of a natural eruption on natural magma in the laboratory. So actually we're right there at the conditions of explosion of the volcano in the laboratory. It means all the things that the laboratory gives us: reproducibility, variability of the input parameters. We have those at our disposal. We can make a science out of volcanic eruptions experimentally. And this is what happens inside that red-hot chamber. This is an example of decompression, and the pressure is dropped on the left-hand side, and you can see what was initially an intact piece of bubbly magma becomes a fragmented material. The diameter of that tube is about 2 centimeters, so you get larger blocks, which we call lapilli, but we also get the fine ash, as you can see here, in the form of what looks like dust, which is freshly produced. It's not dust that was initially sitting on the surface. It's dust that was created by the explosion, okay? Just the way the volcanoes do. I'll show you one more time because that went fast. Try. So this is our porous magma, and now you're about to see the creation of dust at the front. There it goes. So this is fresh ash produced in front of your eyes, the same way that Stromboli produces volcanic ash. And then above that, of course, we have the consequences of volcanism for the Earth system, for us as a species who think we run the Earth system, and for the evolution of the Earth over geological time. And climate impacts of volcanism, we believe, in the past have been massive. We believe that volcanism has pushed us from one era of the Earth's history into the next era of the Earth's history due to the effect of occluding the energy input of the sun. So here you see what happens when we produce this volcanic gas. This is high pressure gas coming out of the chamber. This is in the large tank, which I showed you earlier. And here comes what we call pyroclastic material, hot, broken material. So in nature, these things have a temperature of up to about 600 degrees Celsius. They come down the mountain at about 100 or 200 kilometers per hour. There's no escape. You can sit there and watch and enjoy the show until you're either saved by being in the right place or killed by being in the wrong place. And you can be killed by being burnt to death, by being asphyxiated by the gases, by choking on the ash, by being buried alive, or being hit by a block half the size of this room inside of a cloud. If you've seen the videos, probably you all have, of 9/11 in the United States when the World Trade Center collapsed, and you see the opacity, the fact that you can't see anything when the air is full of dust. It's the same thing when a volcanic edifice collapses. And for experimentalists in geoscience, life is not easy, because none of our colleagues in the field believe that we're doing the right experiment a priori. We always have to really try to convince them. As one of my friends said, Don, we have it much harder than physicists and chemists. We can do the perfect experiment, and then the work begins, because we have to convince all our geologist friends that we did the right experiment to be useful for their purposes. And this is one example of an observation which we discovered without actually inducing it. It was a serendipitous discovery. It was a discovery by accident. We found that we were getting lightning discharges from our fragmentation experiment in the laboratory without applying any voltage. When this happened, we walked across the street in Munich to the Lightning Research Institute, and we said, hi, we have lightning in our experiments. And they said, great, what voltage are you applying? And we said, we're not applying any voltage, we're just blowing up rocks. And the look on their face was enough to tell us that this was something very special that we were observing here. So this is a sketch-up of those experiments, and I'll talk about 3 properties briefly. I'll talk about a fragmentation threshold, I'll talk about how fast the process is, and I'll say something about gas permeability in these experiments. So this is the first plot. It's the threshold. I decided to call it the threshold. It's the minimum pressure differential. This is the vertical scale in megapascals The minimum, if you will, is a kind of a dynamic tensile strength of a volcanic magma. So what does it take to make ash from rock? It takes a rapid decompression, and it takes a certain delta P, or change in stress, and the value of how much drop in stress you need in order to break rock and produce ash, which can then go around the globe, is on the left-hand scale. So you can see that this is plotted versus porosity. These rocks have, or these magmas have bubbles in them containing high-temperature gases, and the porosity, or vesicularity, as we say in geology. I know the biologists use it for the word vesicle for something else, but we use it for bubbles in rocks. This vesicularity in nature runs from 0, which is basically solid rock with no bubbles, all the way to the most extremely expanded magmas, which have up to 80% vesicles. They have more vesicles than actually solid rock, okay? And they go into the stage of polygonal foams and all kinds of things to avoid the geometric problem of having such high porosities. And you can see that the strength, or the threshold, drops from about 30 MPa to about 3 MPa, so about a factor of 10 in the tensile strength of a solid rock with no vesicles, all the way down to something you might use in the bathroom, a pumice for cleaning roughness away from your skin. Yeah? These stones which you can buy in a drugstore. How fast is the process? Now, when you think of volcanism, I don't know if you think fast or slow. I guess you think fast. Certainly, geologically speaking, it's instantaneous compared to all the other things that we worry about, even instantaneous with respect to climate change, where they're always warning you how fast climate change is taking place, right? And certainly instantaneous with respect to the deposition of sediments, to the building of mountain ranges, to the collision of continents, and all these other amazing things which happen in geology. So we're kind of strangers to most of our colleagues in geoscience, because what we study happens immediately, happens within seconds to minutes. And that makes it very useful in geology because it's a time marker. If you find these materials in the field, you know that happened in that day, that year, and you can date it, and you can say what above the age is and what below the age is. It makes volcanology very useful as a tool for other disciplines. But how fast is the process? Now, these surely look fast to you, 150 meters per second down to about 50 meters per second. It's a lot. But you have to bear in mind that the speed of sound in these systems is kilometers per second, like it is in all condensed matter, okay? So all the seismology which is used for looking for oil, if you ever look into a paper on that, you'll see kilometers per second for the speed of the seismic waves. What we're looking at here is slow compared to that, 50 meters per second. What's taking so long? We're decompressing these things. Decompression is simply relieving the stress. Seismic propagation is all to do with the stress, right? The tensorial properties of the P waves and the S waves. Why is it taking 100 times as long to break the stuff as it takes for the acoustic information to go through the stuff? What we think is happening is that there is a crack propagation between bubbles, which has a characteristic length of crack, which has a characteristic time, and which is necessary for the macroscopic disintegration of the material. In fact, these speeds are so low that they're about the same value as our estimates of how fast magma can be delivered to the volcano from below. And we call these things explosive eruptions, but they run on for days and weeks. Once one of these systems gets going, it's like a chemical engineering system which continues to blow out material, and you can collect the layers afterwards and study it in the field. So how can we say explosive if it runs for 10 days? What we think is going on is that there is a steady state which may be obtained between the supply of magma from below and the disintegration of magma from above. So imagine a system where you're blowing material into the volcanic chamber, and it's being eroded from the top at about the same time. That can go on for as long as the supply matches the erosion. It only fails when one of those speeds drops off, stopping the supply or something changing about the ability to erode the material. That's probably why we have long-lived explosive eruptions at all. Third point I mentioned was the permeability. All of the bubbles in these rocks contain gas under pressure. And all you need to do to produce volcanic ash is to decompress. There's actually nothing thermal about it. All you need to do is decompress the material. And the potential energy in the system then, which is released upon decompression, is dominated not by the change in density of the rock itself, but it's dominated by the change in the pressure of the gas, which is in the bubbles. And so what we see here is an energy density, which you can calculate. It's basically the PV energy, the volume of the bubbles in the rock times the pressure of the gas inside of them. And we see that it's a constant as a function of permeability at low values of permeability to the minus 15, 14, 13, but it starts to be a variable when we go to high values of permeability. So what we can do is we can divide the world up here in the middle into an area where a certain value of the energy density corresponds to the fragmentation of the rock here, because the gas is immobile, because the permeability is low. But when we go to the right, what essentially happens in these experiments is the gas loss through permeable flow outruns the need for fragmentation to release the pressure. So essentially we bleed away the driving force for fragmentation through the existing permeable network of bubbles in the rock. And we should recall here that all volcanoes are degassing all the time, uninterrupted. In fact, you can look at a volcanic eruption as if you look at a volcano as a degassing factory of the Earth, you can look at an eruption as an industrial accident during the degassing, where somehow the degassing has been impeded and the gas takes the mountain with it. The gas takes the mountain of magma with it into the atmosphere. It's a mistake, okay, that we have volcanoes that blow up at all. I tried to say this in a provocative way. My geology colleagues would be really angry with me right now. Nothing on Earth is a mistake in the geosphere, but I hope you appreciate what I'm trying to do. The most recent thing that we're doing in this area is to study the acoustic signals, the elastoacoustic signals associated. So this experiment that I showed you with the large tank, with the magma chamber, and with literally producing a volcanic eruption, we can monitor that, we can sensor that up, and we can listen to all of the acoustic information what is giving to us, and it makes a lot of noise. And we can pick that salad, I say, that salad of seismic and acoustic signals apart, and we can discover all the ingredients that they put into the salad. And we discovered that there are elements of the mass flux dynamics, there are elements of stick-slip motion as the material comes out, and there are elements of rock fragmentation and fluid-filled cavity formation. It's complicated. Destroying a mountain is complicated, but we can pick it apart using acoustics. This is what ash looks like. I've been talking very dryly about stuff that I haven't shown you a picture of. This is a transmitted light microscopic view, and you can see the scale there better than I can. And you can see here it's heterogeneous. There are different kinds of particles. You can see some of them are crystals. They have beautiful regular form here and here and here. But some of them have, I would say ugly form. These are shards. These are broken shards of glass. And the glass is the matrix. It is what is carrying the crystals. The crystals are growing from the liquid, but the whole process is so slow that when you blow it out on any given day, you freeze the process immediately, which means you get a lot of information. You get a snapshot of the death of the magma, okay? So, I'm going to jump ahead a little bit. Here we have an example of the properties of these systems. Here what you see is the chemistry versus of the total alkalis from 0 to 18 weight percent. It's basically sodium plus potassium. These rocks are composed of 10 major components. That's what the Earth gives us. It gives us, of course, the entire periodic table, but there are only 10 components which are above 2 weight percent in the mix of what makes volcanic materials on Earth. Everything else is below that and is considered a minor or a trace element, okay? And what you can see here is a selection of just 2 of those elements, total alkalis, versus SiO2. SiO2, extremely important. SiO2, extremely variable, going from 40% to 80%. So from a technical point of view, one sentence, and then I'll answer your question. From a technical point of view, we're going from the contents of silica in slags, which are produced by iron making and so on, all the way up to the content of SiO2 in good glass forming processes. So we're going from the metallurgical extraction industry to the glass industry in the range of what the Earth gives us. Yeah?
The alkali, they're not pure metals, they are salts of some kind. The sodium and the potassium are salts, of course.
They are components in the multi-component liquid. They're not there as external phases. So if I was to write the chemical tally sheet of the composition of a rock, you would see that there's a few percent of sodium, a few percent of potassium, aluminum, titanium, silicon, phosphorus, and so on and so forth, okay?
Not metallic. Not metallic, sorry.
Not metallic, oxides. Thank you very much. Yeah. Everything is oxidized in rocks. There's enough oxygen in Earth that everything above the core of the Earth is present in the form of an oxide with a little bit of other anionic components added into it. That's an interesting discussion about how the composition of the Earth is created and the nucleosynthesis and the capturing of planets and so on. But basically, above the core mantle boundary, everything is an oxide of the Earth, to a first approximation. So we measure the properties of these compositions using materials science methods. And if you would come into our other labs in Munich, you would think you're in a material science institute until we explain what the samples are. So we have high temperature viscometry using concentric cylinder technique. You probably did this experiment in high school. We have micropenetration dilatometry, which allows us to deform very highly viscous materials. And by looking at the viscosity over this very wide range of its value, we can get a global curve for the temperature dependence of the viscosity of the liquids. And you can see that when we try to plot it versus an Arrhenian temperature, we see that very few liquids, in this case just one example, behaves, shows me a value of Arrhenian viscosity temperature dependence, and all of the other samples misbehave. They're horribly curved. They do not express an Arrhenian temperature dependence. So when we do experiments to get close to the glass transition, we can plot the relaxation time versus reciprocal temperature of samples. So here we have SiO2, here we have a sodium alumina silicate, here we have a calcium magnesium silicate. They all have their own individual compositionally variable values of relaxation time versus a reciprocal temperature. And every time we try to measure their properties, our experiments have a value of temperature where we're doing the experiments, but they also have a value of observational time. And sometimes this is not appreciated well enough in the literature, because if you have the goal of understanding the thermodynamic equilibrium properties of these liquids, you must be to the left of these curves. You must be in the relaxed state, and that means you have to choose an experiment which takes a long enough time of observation such that the data you receive are in the relaxed state. Only then can I go into the Earth and try to understand what the relaxed state is in the interior. And this is experimentally what the glass transition looks like. So this is the heat capacity versus temperature. So I'm simply heating something up from a low value on the left, which is the solid state, the glassy state. And then on the right-hand side, I have a high value of the heat capacity, which is the liquid state. And in the middle, I have something very interesting, which is depending on how quickly I heat it and cool it, I get a different value. So I have a hysteresis, I have a path dependence of the CP value depending upon the kinetics of the relaxation of the system. And we develop techniques to be able to do this on natural glasses. So we literally go into the field, take a fresh volcanic glass, bring it back into the laboratory, place it in the calorimeter, then we start to heat it and cool it at different rates and calibrate what this curve looks like depending upon what we did to it. And then we fit this to a kinetic model, and then we solve for the original curve that we got on this sample, which is the first curve we received after we took it out of the field and heated it up. Because glasses have a thermal history. They actually record the cooling rate at which they were produced. And this means that we can now play with the kinetics of how these materials are produced in nature. And you're about to see that glasses turn up in the strangest places. You can probably guess one of them already. Okay, I'm going to jump ahead because I have many, many examples of the details of how we do that work, but I think it's unfair to torture you through all of them. This is the slowest cooled glass we ever found on Earth. This is a rock name. I apologize for it. You can probably guess where it comes from. There's an island south of Italy called Pantelleria, and if you go there, you will find rock of a particular chemistry, and that's this rock. And what you see here is a series of calibration curves of CP versus temperature, and then you see the raw volcanic curve, and you see how far away from this range of cooling rates the actual cooling in nature must have been, because you're way away from an extrapolation of the shape of those curves. So this is the slowest cooled rock we ever found, volcanic rock we found in nature. It comes from a place called Mare Island, New Zealand, right next to White Island, the one that blew up a few years ago and burned a few tourists who were walking across the caldera floor at the time. This is the fastest cooled glass we've ever seen. This is what its curve of CP with temperature looks like. So almost no overshoot, but a huge undershoot when you go into the glass transition. And this undershoot is always a reflection of really fast quenching. This is from a submarine seamount in the Hawaiian chain, where the seawater quenched it very quickly at high pressure, and where its morphology is shards of glass which were between bubbles. So it was already extremely exposed morphologically to the cooling agent, which was high pressure seawater. And you have super fast quenching of these glasses. Okay, I'm going to jump ahead a little more past some of the details that I want to avoid. So we have the opportunity to compare viscosity versus calorimetric glass transition temperatures. It's a way that we can use to obtain the viscosity of heterogeneous samples, and a way that we can use to obtain detailed information on the chemical dependence of viscosity. And we can do this because the relaxation which causes the CP curve to jump, as you've seen, is the same process which causes the rock to physically relax stresses, and therefore is recorded in the viscosity of the material. And here you can see two kinds of data. They look like the same kind of data. You have to look at the axes, and you see this is the log of the viscosity versus reciprocal temperature. You've already seen that kind of plot. And these are the same samples, but it is the glass transition temperature as a function of quench rate. And the message of the story is that the slopes that you get from this are the same as the slopes that you get from this. It means that you can apply an empirical shift factor, you can do calorimetric measurements, and you can get viscosity data. You can do viscosity measurements, and you can infer calorimetric data, because the whole thing is being controlled by one parameter of the whole system, the relaxation time of the liquid. And on the right-hand side here, you can see that we get a shift factor as a function of composition. It varies a little bit, because these curves are now composite curves. The lines are composed of two different kinds of data. You can see black data points here and white data points, and that's the calorimetric and the viscometric data points shifted by a constant factor, same slope, and that allows us to infer one from the other. So recently we've been doing this on extreme compositions, and what you see here is the precision with which we can obtain the difference in glass transition temperature, and you can see it here, 742.8, 745.4. These are extremely precise determinations of the glass relaxation time, and these are a function of the oxidation state of iron in a very, very low silica liquid. So we hyperquench these liquids in the laboratory, we melt them by levitation, and then we quench them. They have containerless freezing, so they're avoiding nucleation. And then we look at their iron oxidation state, and we look at the glass transition as a function of iron oxidation state. And these are the actual raw data which allow you to do this. And then we can take very high temperature superliquidus viscosity data for these systems using concentric cylinder methods, and we can add it to the calorimetric, dilatometric comparison. In other words, using the calorimeter to predict viscosity way down at the glass transition. And we can interpolate the value of the viscosity temperature relationship between these two areas. Now this is extreme. The reason there's no data between here and here is that this will crystallize. These are not good glass formers. So we've driven to an area now where we can even look at really poor glass formers. And another area where we've done a lot of this kind of work is in carbonate liquids. You can actually make glasses out of carbonates. This was speculated about 100 years ago. It was observed 50 years ago, and the glass transition was determined just a few years ago. For the first time ever in physical chemistry, the glass transition of a carbonate glass was determined. And that glass transition allows us to pull these data points off of a calorimetric curve and to complete the curve for the temperature dependence of the viscosity of a carbonate liquid, which, as you can see, is highly, highly non-Arrhenian. The latest kind of calorimetry applied to all of this is a new kind of calorimetry. It's called flash calorimetry. It employs heating and cooling rates of thousands to 10,000s of degrees per second. Now you say to yourself, surely, how in the world can they heat something with 1,000 degrees per second or 10,000 degrees per second? It's done by applying power to a chip, to a microchip upon which the sample sits, and the sample is extremely small. And the heat transfer is extremely efficient. And with those kind of heating and cooling rates, we can manipulate samples that would normally never form a glass, but they will form a glass for the fraction of a second that is required to get these kind of data. And with that, we're able to step into an area which is more physical chemistry than geology, which is, here you have the carbonate melt weight fraction. This is pure carbonate, and over here is pure water. And some of you may know that actually water also, all liquids have a glass transition. Water also has a glass transition. And water glass transition is at about 130, 140 degrees Kelvin. And here you can see the effect of water on the glass transition of a carbonate liquid as this curve falls with the addition of water. And you can see something very interesting, which is that you can continuously extrapolate that to the glass transition of water. So the system water carbonate gives you a continuous variation of glass transition. Why would I be excited about that? Because silicates, normal, volcanic, rock-forming systems, they do not show this. They show a huge cliff between the property values of water and that of hydrous silicate liquids. Now, finally, let's leave the Earth. Getting boring for some of you, I'm sure. When we go to the planets, and when we go to the moon in order to be able to go to the planets, we're faced with very different geological bodies. Nobody knows it better than the geologist who spent all his life studying the Earth and then is confronted with something absolutely different. Even though we knew the morphology of the surface of the moon was different in the early days, in the early stages before we did lunar exploration, the return of samples with the Apollo missions in the 1970s showed us that actually the material that the surface of the planets are made out of, the surface of the moon is made out of, is fundamentally different in its morphology and in its physical origin than that which is on Earth, okay? There are many components to it, but basically the entire surface of the moon is covered with something that we like to call the lunar regolith. And we know, as I said, that the morphology of volcanic systems, volcanism is everywhere on planets, it's everywhere in the solar system, it's everywhere in the exoplanets. Volcanism is one of the great constants of planetary formation. And what you can see here on the left is the so-called pancake domes. Pancake domes, these are a couple hundred kilometers across. They are sitting on the surface of Venus. Nobody knows exactly what they are. We don't have a chemical analysis yet, but people would argue that these things are volcanic, simply because they're round and they have a center, okay? And these pancake domes are unlike anything observed on Earth. There's nothing of this scale or geometry. This is a 3D estimate of what they look like, if you would. So if I would put Hawaii on this diagram, I would get a very different geometry than you would see in this volcanic system. Now, what we have to appreciate about planetary volcanism is that it's not only what's different in the interior of the planet, which matters about it, but also the atmosphere matters. Because as we erupt into, for example, the atmosphere of Venus, then we have 100 bars pressure on the surface of Venus, and we have 400 degrees Celsius. It means that the volcano is being thrown out into conditions which are almost sufficient in pressure and temperature to keep it liquid on the surface of the planet. Okay? So we have very different fates for volcanic systems as we go into these planets. So lunar technologies. There's at least 4 things that we want to do on the moon. And we're going to do it all with local materials. Nobody is going to transport materials to the moon for construction, okay? So what can we do? We need to get oxygen from somewhere to be able to survive on the moon. If you heat up rocks, due to the temperature dependence of their redox behavior, they naturally produce oxygen simply by baking them, roasting them, melting them, heating them up. So there's an unlimited source of oxygen just by cooking rocks, the kind of thing that happens in volcanoes. There's also an unlimited source of water by doing the same thing, because these rocks contain some water. They're not very water rich, but they contain some, and you have the whole planet at your disposal. People, of course, are looking for ice at the South Pole. That may turn out to be the ultimate water source. But if you want to be able to rove over the surface of the moon and choose your landing site, then you may have to go for rock-based water supply. And it, too, is liberated simply by heating the rock. The third thing is the dream that we can pay for it all by doing helium-3 mining on the moon, which has been produced in large quantities on the powder, which exists on the surface of the moon. And the fourth thing is you have to protect whoever goes to the moon from the radiation which hits the surface of the moon, and that means you'll have to build structures. And a few tens of centimeters of silicate rock will do the job for you. But what we will probably do is take the powder, which is the regolith, the soil, if you will, on the surface of the moon, and we will heat it up and try to produce structural materials out of it. Okay? So this is a picture of the regolith. This is the picture showing the powder, which is everywhere on the surface of the moon, a very fine powder. This is what it actually looks like microscopically. Here's the lunar green glass. This is spectacular. It's the lunar orange glass. It was already discovered in the late Apollo missions. It's orange because it has reduced titanium in the titanium 3+ state, which you do not normally have at low pressure in minerals on the surface of the Earth. Titanium is largely oxidized on the Earth. But on the moon, which is more reduced, you do have titanium 3+. And you can see the form in which it's present. These are little glass beads that are present in the dust on the surface of the moon. And inside the glass beads, you have little metallic beads, which are immiscible iron spheres. So we worked already on these lunar orange glass beads, doing a study on their cooling rates, using all that calorimetry that I talked to you about. Yes?
What made the dust? Because there is no air on the moon, so it cannot...
It's not aeolian, yeah. We say aeolian for wind-generated transport of dust. It is volcanic, and it is impact. So there's 2 ways to produce, thank you very much for the question, because it's the right time to say it. There's 2 ways to produce particulate material on the surface of the moon. Number 1 is volcanic eruptions, and there's volcanic material all over the moon. Basically, all of the mare area, the half the surface of the moon, is volcanic. It's basaltic volcanism. And the second way to do it is by impacts. And there's been a long history of impacts on the moon. Just a glance at the morphology of the moon's surface tells you that. All of the craters are produced by impacts, and these impacts produce throw up a lot of dust when they occur. So we have impact, and 30% of the composition of the surface of the moon is glass. Now, this is not the case on Earth, right? It's quartz, feldspar, yeah? Pyroxene, biotite, the rocks that you see if you walk out and see the paving stones on this campus, these granitic rocks. There's no glass in them. They crystallized. But on the moon, you have 30% glass sitting in a powder on the top of the surface of the moon. So just to give you an indication of how complex the history of the moon is, I don't expect you to take anything from this diagram except, wow, that's complicated. It's geology. It's 4.5 billion years old. A lot of things happened in the past, and the moon is a mixture of all of these surface processes. Okay? All right. I'm going to jump ahead a little bit because I know that I'm past my time here slowly. So there's two basic approaches which have been considered to engineer the moon's surface. We all agree that we have to heat up these rocks in order to get the water, in order to get the oxygen, in order to make them formable for structural materials, and maybe to get helium-3 out of them. But the question is, how much and how do you heat up the surface of these moon rocks? What technology do you take to the moon? And it's going to have to be a very robust technology, because if something goes wrong, it's not going to be easy to fix. And there's two philosophies, basically. The first philosophy is you go to very high temperature and you do a kind of 3D printing approach. In other words, you heat these liquids up so much that they basically pour like water, and then you can ooze them out of some kind of device which will allow you to form the 3D things that you want to build with. Okay? The second way, which is considered to be taken, is sintering. Sintering means you take this powder material, you put it in the form that you want to have it inside a container, and you bake it just enough that this 30% glass does the work, gets sticky at the glass transition temperature, and glues the whole thing together in the form of a composite, partially glassy building block. Okay? Those are very different ways of doing it, because here you have very high energy costs to get to the very high temperature. Here you have low energy costs. And here you have something which is going to be cooled 1,000 degrees from its production temperature down to room temperature, or lunar temperature. What's going to happen on the way? Whereas here you just, you utilize the fact that you have glass already in the regolith. You only have to go up to a few hundred degrees Celsius. Now, there's one issue on the surface of the moon, which is, like many of the planets in the solar system, there's a dichotomy about the morphology of the surface of the planet. The Earth has it. The Earth is the oceans and the continents. We used to think, before I was born, that under the oceans were the same rocks as on the continents. That was the initial idea up to early 1960. And then through plate tectonics and through geomagnetic mapping of the seafloor, we realized, no. The seafloor is completely different, composed of completely different rocks than the continents. So the Earth has two kinds. The Earth has the lunar mare. They're just underwater, okay? So you have, this planet has been surfaced by two components, the high stuff and the low stuff. Same thing on the moon. You have the lunar mare, the black. When you look up to the moon the next time, the dark stuff, that's basaltic volcanic rock, and the light stuff, that is deeply crystallized feldspar-rich rock that we call anorthosite. Canada is full of it, and it's several places on Earth where we encounter this stuff, okay? Mars also has two. It has a north and south hemisphere, which they have completely different topography and completely different chemistry. So there's something about building planets which leads to this, or this, or this, okay? Maybe it's the last great impact or something like that. Why am I referring to all of this? Because the materials which form the lunar mare are thin flowing liquids. They're like basalt from Hawaii. They will flow 50 kilometers to the sea at low viscosity, and you can certainly manipulate those things with high temperature 3D printing, no problem. As long as you keep them hot, they'll flow forever. But the lunar highlands are composed of anorthosites, which have a much higher viscosity. They will never flow. The only chance you have of making structural material out of these high viscosity liquids is if you bake them in a sintering system where the pre-existing glass will allow the sintering to occur. And these are just viscosity data to make the point where you can see here logarithmic units of viscosity, and you can see the basaltic systems at the bottom, and you can see the lunar highlands at the top. So if you go to the wrong place on the moon with the wrong technology, it's not going to work. So the message is, you have to have the geology of the moon already figured out, and you have to have done tests on local surface material, which is highly variable. I remind you of that ugly geological plot I showed you earlier, before you decide what technology to send where on the moon. And these things are not 500 meters from each other, yeah? They may be 1,000 kilometers from each other. So you're not just going to drive over and do it there. You have to decide already, are you going to the Mare? Are you going to the lunar highlands? What are the properties of those local regoliths? And can I use the technology that I've chosen to develop over the past 20 or 30 years? So it's a generational challenge for us to successfully be able to engineer the surface of the moon. It's going to happen. It's going to be multiple approaches because there are multiple people who are funding this. There are different countries who are funding it. The Chinese will have their bases. They will have their technologies, which they try to refine. The Americans will have theirs, and other parts of the globe will have theirs as well. Yes?
How large are the different areas of the moon with different composition? Like, what are the odds that
Tens to hundreds of kilometers.
so there's an issue that like you'll run out of space to design technology?
Sorry?
So there's not an issue that you'll run out of space that you design your technology for?
No. If I understood you correctly, the units, which would be raw materials, here or there, they're unlimited for the purpose of the amount of material that we have to use. Think about it as going to Canada 250 years ago and looking for gold or other.
So area doesn't really matter.
No, but location does. That's what I'm. Yeah.
So you mentioned cooling, first heating and cooling the rocks, but there is no air on the moon, so the cooling would have to be extremely slow, only radiative, or would you cool it somewhere in-house, so to speak, with air in the station?
The cooling will be relatively slow, but the real question is, will these materials nucleate and crystallize upon cooling? And that also depends upon whether there's an atmosphere and whether there are active gas species to serve as a nucleus enhancing sites. So the real question is, what happens in terms of phase state when you cool it? You don't care how fast or how slow you cool it if you get the same stuff at the end, right?
Please finish lecture, our professor, that, we will,
One-
you can ask questions after
It's
lecture,
okay. It's good. One last slide to say that it's not only, two last slides, sorry. We live in an age, when I was born, we had geological knowledge of we had one example. That was it, the Earth. When I was born, the best geologists in the world were all Canadian, and they had Canada at their disposal. There were a few good Russian geologists, a few good Australian geologists. They were all characterized by having vast countries to be able to map, but that was it. That was the limit of our geological knowledge. And we really didn't even, I was born in 1958, we didn't even know how the Earth worked in 1958. We hadn't even really accepted plate tectonics and the drift of continents, which were right in front of our eyes, okay? Then we go to the moon in the 1970s, right? I was a teenager, it was a fantastic time, and we have two worlds that we can compare. Well, I can tell you scientifically, the difference between one object of investigation and two objects of investigation is philosophically enormous, because now you can start comparing what was missing in one, what was present in the other, why are they different, what does it all mean? And it goes as far as the spectacular inference that the moon was produced by a collision of a Mars-sized body with the Earth, and that the moon comes from the Earth. I mean, you couldn't ask for a more spectacular interpretation based upon having gone to the moon and discovered that all the iron is missing. And where is the iron? The iron is in the Earth's core already. So geologists are capable of fantastic interpretations based upon very few data points. Now we're in the age of exoplanets. Sure, we don't have a lot of data on these exoplanets. We're basically getting their atmospheres first. But eventually, I am told, we will get the trace gases and we will get the trace metals, which are volatile in the atmospheres. And more we'll be able to constrain what are now the thousands of rocky exoplanets that we know exist and have been observed. And that number grows every week. And satellites go up every 5 years, which are better than, telescopes, which are better than the last ones. So in my lifetime, we've gone from one planet of investigation to in the extreme thousands. That's amazing. It's never going to happen again. It happened just now. And I can tell you, although I look very old, it was yesterday. So you're living on a threshold of understanding of planetary formation, which will have many sources of data in the near future. One, further exoplanet research, another actually going back to the moon, and this time, on a mission and in a competitive sense, and of course going on to Mars. And we will go because people are driven to know whether there's any evidence of ancient life on Mars. And the only way you will ultimately convince geologists yes or no is to have a rock in the hand, which demonstrates some sort of evidence of previous life. But we'll come back to Earth because we want to stay applied in some ways, and I just give you one more pitch for what is on the horizon, and that is innovative geothermal analysis. So geothermal energy, as you probably know, is underused almost everywhere in the world. One example which is not that way is Iceland. Iceland uses geothermal energy very effectively, and in fact, Iceland has a department of the government which is responsible for volcanic hazards and geothermal resources. It's fantastic. So that means that the people who are responsible for generating money with power generation are also responsible for understanding how the volcanoes work. So what do they think of? The obvious thing, they want to drill into a volcano and make energy on the volcano. But the question is, can you drill into a volcano? What happens if you drill into a volcano? Well, we know because by accident, we've done it several times in the last 30 years. So you're drilling in above a volcano, you think it should be switched off, and suddenly, oops, something is coming up, literally coming up and out of the drill hole. And you produce a little mini eruption locally. So we want to make a science out of this. We want to actually do magma engineering by going into magma, doing the science, but also at the same time pulling out 10 times the geothermal energy, which you get, for example, in Munich, when you drill into some boring glacial deposits, which are south of the city at 150 degrees Celsius. Here we want to go to 900 degrees Celsius. So I know I've tortured you with the diversity of what I've shown you. I'm finished now. It's my last slide. I'm happy to take as much time as we have for any questions you might have, and I hope at least all of you enjoyed one of the slides that I showed you and that it remains in your memory. Thank you very much.
Thank you, Professor, for a very nice presentation. And now it's time for questions. Do we have any questions? Oh, yeah.
Thank you for a very interesting presentation. I think your experiments on modeling volcanoes in laboratory is so exciting as modeling high velocity impact. And what is, if you could say a little bit more on the scale effect in your experiments, because when you transit from laboratory to especially porous or crack material, this transition is important when you go to a mountain size volume.
Right, so very clear. So the question is about, for example, length scale. So very clearly, we're not working on the length scale of the entire object, which is in the Earth, which, although we do not know exactly what the length scale of the reservoir is, which is feeding the volcano, it's not necessarily as wide as the mountain. It could just be 50 meters or something wide, but nevertheless, we're still a couple log units away from that. So the question is, how do we deal with the fact that we're on a, if I've understood your question, how do we deal with the fact that the length scale that we have available in the laboratory is quite different from the length scale of the volcano in nature? And my answer to that, and I'll be interested to hear your reaction, is that what we're really interested in is the length scale of the mechanism of the material mechanism of failure. And the length scale of the material mechanism of failure for us is the bubble spacing in the magma which we're about to destroy. So essentially we're talking, remember I said that the process is very slow compared to the acoustic velocities. Why is it so slow? Why doesn't it simply go with the acoustic velocity? And we infer that it is a crack propagation mechanism between adjacent bubbles which is causing them failure. And so if we can have the same scale of that bubble spacing in the same material, at the same temperature and the same pressure, I would argue that we are scaled to the effective length which is important for at least the material transition into fragmentation. We may not be scaled in all of the dynamics of how that material is coming out of the pipe, because that has to do with the dimensions of the conduit. It has to do with the absolute diameter of the conduit, because that's the amount of edge to center, if you will. And it has to do with the smoothness of the conduit, which is more rough in nature. So there's a lot of open questions about how you scale the dynamics of the flow. But whether or not you get a flow, I think we have that part under control.
Okay, thank you. Any extra questions? No? Okay. We mix lecture with question. Oh, here.
Thank you very much for a very interesting lecture. I'm Katarzyna, I'm a member of Academia Europea, so really a great respect about diversity of your studies. I'm a chemical engineer, so I'm interested in the chemical composition of volcano ash. When I have been to Sicily, and there is Etna ash, Sicily is a very green island. Another example, Madeira, which is volcano island. The content of volcano ash is potassium, which is essential macronutrient, also magnesium, calcium, and also silicon, which acts protectively to plants. I would like to ask you a question, whether there have been any plans to use volcano ash as the resource of chemical elements like potassium. Now we have a very serious geopolitical problem with potassium, as the ores of potash are in Belarus and Russia. So maybe volcano ash could become the source of important elements, important raw materials like potassium. Thank you.
Okay, you also have the potash from Canada, right? From Saskatchewan, and I think there's enough there for everybody. So I think potash, what's normally mined is sodium chloride and potassium chloride as a coarse-grained ore, which means that liberating potassium is almost trivial. You just have to throw it in water and it dissolves, right? The potassium, which is in volcanic rocks, as you saw in my total alkalized plot, maybe you could guess, it runs from a few percent of potassium. In Etna, there would be a few percent of potassium oxide, always oxides, to that previous question, all the way up to, in the extreme case, maybe 10% of potassium oxide. In the volcanic rocks of central Italy, the Roman province, these things are very potassium rich. How easily extractable that is and whether that's a competitive alternative to potash is a question I've heard for the first time and I don't know the answer to. But I'm dreaming of these fantastic samples I had in my hands 40 years ago of potash from Saskatchewan, where the crystals are as large as my fingernail and where they are chlorides, which makes them really incredibly accessible as a source of potassium. But you didn't mention one element. Phosphorus is also in these rocks. Now, phosphorus can be 0.5% or 1% of the rock. We recently published a few papers on the availability of phosphorus for prebiotic chemistry, trying to find that path, because we think that, well, some of us think that life originated in the rocks somehow, somewhere. And if you want to do that, what are the steps that you need, and what is the environment that you need of gradients and salinity and temperature and reproducibility of generating intermediate molecules? And where do you get the damn phosphorus from? Because phosphorus is something which is essential to life. So these rocks contain phosphorus as well. When these explosive eruptions take place, it's in the form of a finely divided powder. It lies over the entire mountain, and if you've been to Indonesia or if you've heard about it, people live there on extremely small plots of land where they harvest several times a year because they have such fantastic fertility of the soil. The problem is the closer to the volcano, the more fertile, and then you have the issue that volcano eventually is a problem. So it's a big socio-political issue as well as to where people do this in those countries. So you sparked an interesting question, and I'll think about that, and whether or not potassium is easily liberated, or whether there's any literature on whether it's easier to liberate potassium from these volcanic rocks. It's in volcanic rocks, of course, in the form of silicates, either minerals or glasses. So it's there next to a lot of other major components which are neighbors. Interesting question.
Thank you. Any other question? Be the last one, okay? Professor, it will be the last question.
Okay, thank you for the presentation. I have a question about the technologies to manufacture materials from the rocks. Do you have opportunity to work or see the example of technology, the device for the 3D printing with the lunar logarithm analog, and how what is the stage of the development right now?
So what I know best is the high temperature 3D printing side of things, because we've been working in collaboration with people at the Technical University of Berlin. And I'm somebody who melts rocks every day for the last 30 years. I know that sounds crazy, but it really is science, people. And therefore, I know how these things behave. I know how they misbehave. I know what can go wrong, and I know if I get a phone call from my lab, or if I get a phone call from Berlin, it's because something failed, and you're dealing with high temperature liquids. These high temperature liquids are corrosive to a lot of materials that they're exposed to. So if something goes wrong, it's a major problem, and it usually crashes the whole system. So I don't want to condemn this approach to producing things on the moon. Maybe it will work, but I have enough experience of things going wrong that I'm very concerned that it will be impeded by accidental interruptions. And what if that's on the moon? I mean, what are you going to do? Are you going to send up 50 prototypes so that you just go to the next device? Probably. It would be an incredibly wasteful endeavor, perhaps, in terms of the materials involved. As far as annealing the bricks goes, I don't have any direct experience of the technology, but we have a vast amount of information now on modeling the sintering rates of glass-based silicates. There's review papers on it, which basically, with models and with dimensionless analysis, which allows us basically to tell you how effectively you can sinter just about any glass-bearing silicic rock.
Thank you.
Is there a simple measure of volcanic activity of a planet? Like I can imagine, for example, the amount of stuff that's thrown to the atmosphere per square kilometers of surface, something like this. And then if there is a measure like this, how does the volcanic activity of the Earth change throughout its history? And how does it compare to other bodies that are possible or studied hypothetically?
Yeah. So what we do have is, the simplest thing we can do is map the surface of a planet, because that's what we do already for decades, and we determine how much of that surface we believe is of volcanic origin. That gives us some sort of time integration of the amount of volcanism that we can at least infer from the present surface of the planet. So for example, the flybys of Mercury, when they occurred, what was it, 15 or 20 years ago now, and people were shocked at how much volcanism there was on Mercury. There was one fellow who put up his finger and said, I've been publishing this for the last 30 years. Mercury is the most volcanic planet in the solar system. So we can infer the fraction of the planet which is volcanic in origin. We can infer the depth of the regolith. Much beyond that, we cannot quantify. Most of the volcanism which occurs on the moon, of course, is ancient volcanism. The moon is, we think, is dead. By the way, the definition of a dead planet for us geologists has nothing to do with biology. It's volcanism, okay? Once a planet no longer has volcanism, we call it a dead planet. That's what I learned when I was 17. I just want to throw that out there in the age of bioscience. So with regard to the differences over time, geological time, we do believe that we've pushed the Earth in and out of, we have a snowball Earth phase where we believe that there was glaciation over the entire planet, and we believe that that was produced by excessive volcanism at a time in the Earth's past. We do not have a fine resolution integration of the amount of volcanism with geological time. We only have sort of signposts along the way where we can say we believe the only way to explain what happened there to the surface temperatures and the kind of rocks which were produced and therefore allow us to infer the surface temperatures must have been related to major volcanism. That's the kind of level of resolution that we have in the arguments for the variation of volcanism in the Earth's past. Generally speaking, we would expect that volcanism is decreasing with time on the Earth, simply because the heat in the Earth is decreasing with time, because a lot of heat in the Earth is related to very long half-life radioactivity. It's quite amazing, really. The Earth gives us all these tools for dating the Earth, which are related to the fact that there are parent-daughter isotope systems which are half the age of the Earth. If we didn't have them, we wouldn't be able to date the Earth, okay? So we have a number of those, which gives us an indication that there has been more radioactive parent in the past, of course, as the half-life of the reaction goes forward. And of course, many of the parent-daughter systems have died out with shorter half-lives, aluminum and some other, and xenon and other short-lived radioactive isotopes. So the Earth has cooled over time. We think volcanism has decreased over time. We have to be a little bit careful because volcanism is not one thing, it's several things on the Earth. It's the melting of the mantle. It's also the melting of the crust. And of course, the melting of the crust takes place under different temperatures than the melting of the mantle and is a secondary process which only began after we created the Earth's crust. So it's not simply a global drop of volcanism with time. It has a few bumps along the way. But you asked two questions which I cannot answer in their entirety. We simply don't have a completely global view of those two elements, of the time dependence and the planetary comparison of the amount of volcanism. We don't know how much of the dust on the surface of Mars is volcanic. There, we talk about aeolian things all the time because everybody talks about dust storms on Mars, right? But where did the dust come from in the first place? Is it all weathering or is some of it volcanic as well? And we'll only know when we get there and have a sample in our hands.
Thank you very much. We use time for questions that we can finish. Professor, thank you very much for a very interesting lecture that we can finish.
Thank you for the excellent questions.